Hi, my name is Sarah Farina. On behalf of my team, I would like to welcome you to our video about our power station design. Our team comprises of 4 members, and that includes myself, Junhao, Celestine, and Surya. The aim of our report was to design a steam power station that will sufficiently supply 280 megawatts of electricity to the Lumut Naval Base located in Perak and its town surrounding it. The importance of the study is to gain a deeper knowledge and comprehension of thermodynamics that will be applied, and understanding the fundamentals of safety when designing a power station. The steam power station is, as a whole, an electric generator that utilizes steam as its working fluid. In a steam power station, there are 4 main components that will effectively produce useful work, which include the turbine, condenser, boiler, and compressor. In a typical power station, water is heated in the boiler to convert it to steam, which will then move through a turbine. Since leaving the boiler, heated steam contains high amounts of energy and pressure and thus will expand in volume, simultaneously using both pressure and heat energy when it passes through the turbine. This mechanism extracts kinetic energy that will be converted into useful electricity. Following that, once the steam leaves the turbine, the steam will undergo condensation when passed through the condenser that will cool the steam. Condensers are utilized to reuse the steam for it to be safely and continuously utilized in the cycle, while also maximizing the efficiency of the turbine by preserving a vacuum in the system. Lastly, the condensed steam will pass through a compressor where it increases the pressure of the steam.
The proposed power plant we designed consists of 6 units of Keppel Wire TRL power 50 MW high-tech steam turbine, a boiler, a cooler, the furnace or pump, the generator, and the piping system. The work fluid utilized in this system is water, which is the same as the cooling medium we use in the cooler. The turbine uses the hot steam produced by the boiler to initiate shaft work and generate electrical power. The heat energy that is used to heat up the steam is provided by the furnace by burning the fuel. On the bottom, the cooler will transfer the heat from hot stream coming from turbine to a low temperature cooling medium in order to reject excessive heat out of the system, changing the phase of the hot stream from saturated liquid vapor mixture to saturated liquid. Then, the working fluid will enter a pump that will raise the pressure of the fluid before entering the boiler.
Hi, I'm Celestine. Next, I will share about the calculation and result part for our project. In this project, there are some assumptions that made. The first assumption is steady flow process throughout the device in order to make the calculation easier. The second assumption is well-insulated turbine in order to let the asymptotic process occur. The third assumption is there is no leakage in the pipe, which means there will be no change in mass product throughout the power plant. The fourth assumption is the pipe is frictionless, so there will be no energy loss due to the friction when the fluid is flowing throughout the power plant. The fifth assumption is the mass product that enters the turbine is 3,500,000 kg per hour, which determined by using the ICON simulation software in order to get the design power, which is 280 megawatts. The sixth assumption is the change in gravitational potential energy and kinetic energy is negligible. The seventh assumption is the efficiency of the pump is 80% in order to reduce the energy loss to the surrounding. The eighth assumption is the change in pressure in boiler and cooler is negligible in order to make the calculation easier. The calculation is made based on the result from ICON simulation software. The actual power produced is 320.12 megawatts. According to Association 2018, the heat value for the low sulfur grade coal is 25 megajoule per kilogram. So, the amount of the coal required per second is 79.04 kg. The steam that generated from the power plant is 3,507 m3 per hour. The thermal efficiency for the power plant is 0.2 and the total work required to run the cycle is 40.44 megawatts. We also made manual calculation in order to compare the value from the ICON simulation software. From the manual calculation, we can get easier, smoother answer from ICON. That's all from me. Thank you.
Hello, my name is Surya and I will talk about the recommendation and conclusion of this project. First and foremost, the power plant is designed for the Lumut Naval Base and Town consists of 6 unit Kempo Waja TRL 12 50 megawatts high-tech steam turbine, 1 boiler, 1 cooler, 1 furnace, 1 pump, 1 generator and piping systems to produce the desired electricity of 280 megawatts. By using the Icon simulation software, we can get all the values from it. The total work that is required to run the process is 40.44 megawatts and the thermal efficiency of the steam power plant is 0.2. The heat that enters the power plant is 1976.11 megawatt, while the heat exiting from the power plant is 1655.83 megawatts. The electricity that generated by the power plant is sufficient to supply the actual power to Lumot Naval Base and its town, which is 320.12 megawatts. The power plant that we designed is using simple Rankine's cycle which has limited thermal efficiency. The thermal efficiency can be increased by reheating Rankine's cycle and regenerative Rankine's cycle. To increase the thermal efficiency of the power plant, we must lower the condenser's pressure. Secondly, the steam should be in high temperature to increase the thermal efficiency of the power plant, and this would help to evaluate the average steam temperature during the heat addition. Thank you.